Today with us we have Professor Christopher A. Schuh, who is the Denai and Vasilis Salapatas Professor of Metallurgy in the Department of Material Science and Engineering at MIT. His academic training in material science and engineering focused on metals, including their processing, microstructure, and mechanics. He earned his bachelor's from the University of Illinois at Urbana-Champaign in 1997 and his PhD from Northwestern University in 2001. And he held the Ernesto Lawrence postdoctoral fellowship here at Lawrence Livermore National Laboratory from 2001 to 2002, prior to joining the MIT faculty in 2002. His research is focused on structural metallurgy and seeks to control disorder in metallic microstructures for the purpose of optimizing mechanical properties. Much of his work is on the design and control of grain boundary structure and chemistry. He's founded a number of metallurgical companies. His first MIT spin-out company, Xtalic Corporation, commercialized a process from his laboratory to control the internal structure in metal electroplated coatings down to the nanometer scale, producing exceptional mechanical and functional properties. And these have been deployed in applications ranging from machine components to automated parts to electronics, and are in wide and growing use around the globe. He also co-founded Desktop Metal, a metal additive manufacturing company producing 3D metal printers that address markets ranging from prototyping to shop scale to production scale. In 2011, he was appointed head of the Department of Material Science and Engineering at MIT, and a position he has filled until the end of 2019. I am happy that he is with us today to give us his talk. Please be aware that this talk is being recorded. If you're uncomfortable with that, please log out. And also, it's an unclassified meeting with people logged in from outside the lab, so please be aware of any export control issues. If you have any questions, feel free to enter them in the chat field or signal to me that you'd like to ask it verbally. And for the most part, we'll hold questions to the end. Otherwise, please sit back and enjoy. I'll pass it off.
All right, great. Thank you so much. Thanks for the introduction. Can you hear me okay? And can you see this laser pointer on these slides?
Yes.
Yeah. Okay, fantastic. Thanks. So I really do appreciate the introduction. It's great to be here. I appreciate having this opportunity. And I have to say, I regret that I didn't get to come to sunny California to deliver the talk. It would have been great, but glad to do this anyway in any context. One thing that happened here is it got me sort of reminiscing about my time when I was at the lab. I was in Livermore in 2001, and so it's actually like 20 years, like almost to the day that I went to Livermore. And it got me thinking about my trajectory through this field and how I got to where I am. And so I thought I'd start by sort of sharing a little bit of my trajectory as it pertains to my topic today. And I will introduce all the people on this slide to you as we go into the talk. But for the moment, let me just give you my background so you know where I'm coming from. So I'm a mechanical metallurgist. I work on metals and I care about their mechanical properties. And I've been working on mechanical testing of metals for 25 years. And when I think about it, my trajectory through the space of mechanical testing has basically been one of seeking ever higher strain rates. So in 2001, as I was coming to Lawrence Livermore, I had just completed my PhD. And for that, I studied the creep of metals. So I used large inch scale mechanical specimens, and I would apply small loads to them at high temperatures, and they would deform at exceedingly slow velocities, right? So in terms of mechanical testing, we're talking about the lowest velocities, 10 to the minus sixth per second and slower, and large scale samples. And as much as I learned in that experience, as much as I loved my PhD work, it was frustratingly slow. You could wait weeks or months for a single data point for a creep experiment. And so I was always trying to push to higher rates when I was doing that work. But I never really got to anything close to, an interesting strain rate. So when I came to Livermore, one of the things I was interested in is sort of having higher throughput and higher rates. And at that time, nanoindentation had just really come online as a high throughput mechanical testing tool. And I worked with TG&E at the lab. And to me, this was a change in many ways because, first of all, it's high throughput, as I said. So instead of conducting one test over the period of weeks, I might do thousands of tests in a period of weeks. So I could really generate a lot of data. And TG and I were also interested in doing high strain rate work. And so we pushed nano indentation up to really its limits, which was maybe 10 to the 2 per second as a strain rate. And we could study things like the transition from serrated flow to smooth flow in this metallic glass type sample. And so we really, nano indentation has a natural strain rate that's on the order of 1 per second. And we really pushed that as much as we could. When I got to MIT, I had already caught the bug that I enjoyed doing small size scales and higher rates. And of course, it's the ratio of the velocity and the sample dimension that gives you the rate, right? So the strain rates are these contours here. And it's sort of a funny thing that if you're doing a creep test or you're doing a nano indentation, uh, really the entire change in strain rate is because you've changed the size of the sample. So you'll go to small samples, but you don't really change the velocity. Those things happen at almost the same velocity. That's kind of amazing. And so when I got to MIT, I started thinking about how do I take micro scale mechanical testing and push it to even higher rates. And so one of the projects I worked on there in my first 5 or 6 years was to help develop what is now known as the dynamic indentation test. And dynamic indentation is essentially nano indentation, but with attach it to a pendulum and give it a little bit of a swing. And so now you indent something, but you're able to measure the velocity of the indenter as it strikes the substrate and then as it rebounds from the substrate. And with that kind of technology, you can push this up a few more orders of magnitude. And now, at the micro scale, you're measuring things that have strain rates comparable to like a Kolsky bar or a flyer plate impact or something like that. So you get genuine high rate data at the micro and nano scale. So that's sort of my trajectory in mechanical testing until a critical moment hit about maybe 4 or 5 years ago when I started interacting with Keith Nelson. Keith is my colleague in the chemistry department, and I started talking to him and his postdoc, David Vaisey, and my postdoc, Mustafa Hassani. We started talking regularly because I'm interested in mechanical testing, and these guys in their lab, they're chemists and they do a lot of optics work, and they're really experts with laser systems. And they had made a really interesting little system in their lab where they were using a laser pulse to ablate gold. So that's, of course, a well-known phenomenon that you can ablate a tiny volume of gold with a nanosecond laser pulse. But what these guys had done is they had turned that into a method of doing mechanical work by encapsulating it behind a film of polyurea elastomer, right? So that when you ablate that gold and you get this explosive volume expansion, you're inflating a little balloon here at the nanosecond time scale. And they were using that to launch little particles. So if you characterize a particle, put it underneath that laser, you can now blast it off with that laser. And because they're working on an optics table, they can also then time it so that they're able to use a secondary laser as an imaging opportunity so they can take pictures of this thing. And when we started talking, they were in the throes of setting up a new camera, which had an incredible 3 nanosecond interframe time spacing so that you can get incredible fidelity measurements of particles as they fly and as they crash into a substrate. So this, as a mechanical testing kind of person, I looked at this and I said, wow, this is it, because look where this falls on the map over here. We're talking now about doing essentially micro or nanoscale indentations, but we're able to launch these particles at velocities that are in the hundreds of meters per second up to kilometers per second. And in fact, nothing I talk about today, nothing will be at a strain rate below 10 to the sixth per second. So very high strain rate testing. In fact, higher than you can normally get quantitative data with like a Kolsky bar or a impact system. So that's what I'm going to talk about today. So the first thing I want to do is show you how we've been working to turn this into a quantitative tool. What I really want to do is measure mechanical properties at these rates. And so again, Mustafa and David and Keith were the core team that started this thing. And I'll start by showing you a simple example of how you literally can use this test as a high strain rate nano indentation test. And by the way, we refer to this apparatus as the LIPIT. It's an affectionate little title. It stands for Laser Induced Particle Impact Test. And the raw output of a LIPIT test is shown here. So here's one of these little movies. And in this case, we are using a hard indenter material. So we've selected sapphire particles, alumina particles, which are spherical and very, very hard. And we're launching them to indent a copper substrate, so a soft metal. We collect a bunch of video frames, which allows us to measure the velocity of that particle as it flies in and strikes the substrate. And then we can also measure the outbound velocity. And by knowing the inbound and the outbound, of course, now we can get a kinetic energy deposited in the substrate there. And I'll just point out that the entire test here is like, it's about a microsecond in total time, so very short time scales. Also, like nanoindentation, this test platform is a really high throughput apparatus. So when we go to test the properties of copper, like I just showed you, we don't just do one of these tests, but with the same tiny little sample and a handful of alumina powders, we can repeat the same test over and over and over and get dozens of data points. And we can even vary the impact velocity so as to assemble a response curve like the one shown here. I'm showing the coefficient of restitution. That would be the outbound velocity divided by the inbound velocity. And so this is sort of a measure of the bounce, if you will. So we're talking about having bouncier things here, and then as we go to high velocities, we get less and less bounce. And that's a signature that we're doing more and more plastic work to that copper substrate. So this is a very quantitative test. In fact, you can see experimental error bars on these points, but they're very, very small. So we actually have a very high fidelity measurement of the plastic work that we've done to the substrate. And if you marry that now with some microscopy, you take this sample after you shoot it, and like a hardness test, you go look at it afterwards. And in fact, you don't just look at it, but you measure the damage you've done. In this case, we're using laser scanning confocal microscopy to measure very precisely the volume of that indentation. And if you know the plastic work and you know the volume of the indentation, that is literally the definition of hardness, which lets us extract hardness values. So we have now the hardness of copper here, the hardness of iron, with the notable exception that our hardness values are acquired at a strain rate of 10 to the 7th to 10 to the 8th per second. So extremely high strain rate, quantitative mechanical testing. And now that you have data like these, you can start asking questions like, how relevant are these data? How do they compare to other modes of hardness testing down in the quasi-static range or maybe in the dynamic range? Recent Kolsky-Bar work has sort of debated whether there is an uptick in rate hardening in metals like copper and iron. And our data here now can be compared against these. And based on this extrapolation, it kind of looks like we would support an interpretation of an uptick in the rate hardening at these very high strain rates. So quantitative studies are now possible. And to me, this is now a really interesting tool to go into the world and start to solve problems and really answer some interesting questions. So at this point, we were looking around and looking for applications where this tool could really do something useful with quantitative measurement. And at this point, I want to introduce some collaborators. So Aaron Nardi and Vic Champagne are at the Army Research Lab. And we started working with them. And then at the same time, we brought in some students, Yu-Chen Sun and Jasper Leonard. And Yu-Chen, by the way, is on his way to Livermore. He's joining the staff there. So he's joining up as a postdoc. So some tech transfer here. But the connection to ARL has been really useful because these guys are working on an industrial process that is just a slam dunk fit for lipid testing such as we do. In fact, Vic Champagne at ARL is sort of famous in the world of cold spray manufacturing. If you've never heard of cold spray manufacturing, it's kind of like any other particle deposition process. So think, if you will, spray paint or plasma spray, something like that. You're spraying metal powders and you're rastering it over a surface to deposit a coating. The key difference in the process of cold spray is that this is a supersonic spray. So they intentionally incorporate a supersonic nozzle and they get the powder flying at supersonic speeds. And the reason is that when metal gets flying that fast, upon impact, there's so much plasticity that you can actually get particles to stick and grow a coating by virtue of their kinetic energy alone. So you don't even really need to heat these things. You can heat them mildly, but you don't melt them. You just literally spray solid particles and you stick them and you grow them into coatings. And you can do it for lots of different metals and composites. And this really is a technology that is taking off and it's becoming quite a large industry now. And of course, this industry has a lot of needs to understand how it works. And the process is so fast, they actually don't know how it works. They can't see it, right? It's just too fast. And so they know there are windows of deposition where particles stick instead of bouncing, or they stick instead of eroding. And so they'd like to understand, what are those windows? What are the physics? How can we predict and understand and control the process? So this collaboration led us to do a lot of work on what I call matched metal pairs. So you're shooting a metal at itself, basically. So now I'm launching aluminum particles. They are impacting aluminum substrates, and I'm measuring the mechanical response of like on like during one of these impacts. So again, we would do a high throughput kind of study where we'd shoot a few dozen shots that are nominally identical. The only exception is that we do this at different velocities. So now we get a response curve. So here we're measuring the bounce, and again, we're getting less and less bounce as we go faster, and that is a signature of plasticity. And I'll show you in a few moments that we can use this as a way to measure plastic properties. And then, of course, there's also new physics that we care about. If we shoot these things fast enough, they don't bounce at all. They stick to the substrate. And of course, understanding that sticking really is important in the field of cold spray. So we do this not just on aluminum, but on alloys and on other metals as shown here. Again, high throughput, you can get a lot of data reasonably quickly. And they're all similar, but of course different in their details. And what we'd like to understand is, what are the physics controlling those details? How can we predict the onset of bonding, for example? Well, the first thing you can do with these data is, again, you can sort of analyze them quantitatively and try to extract some information about plasticity. And for this purpose, we found it useful to use this model that was developed by Wu et al. In 2003. This is a really nice, very simple model that I think it captures the essential physics while ignoring a lot of the details. So this model is based on a whole bunch of finite element analysis that Wu did of a whole bunch of different materials properties impacting, and it's again a matched material impact situation. But what they're modeling here is not the full complex problem that could occur. So they're not including work hardening and rate hardening and heating, adiabatic heating and softening. So there's a whole bunch of details that are sort of shoved under the hood and subsumed into a single effective yield stress for an elastic, perfectly plastic impact. So this is sort of a baseline plasticity model. But this model is really powerful because whether the target is allowed to deform or the particle is allowed to deform, all the data collapse onto a very simple and very beautiful power law. And that power law holds over orders of magnitude of velocity. So we really have a useful tool now, because if we have a power law like this, it tells us what the effective yield strength is. And in fact, that's exactly the way it looks. When we do these experiments shooting metals at the same material substrate, we do in fact collect response curves which lie on that power law. So you can convincingly fit those data with this power law, and you can now extract from these tests what the prevailing yield strength is, or the average yield behavior describing the entire impact event. So here they are for copper, nickel, aluminum, zinc. We've been able to fit and measure the dynamic yield strength. And again, just remember, this is a yield strength measurement at 10 to the 7th per second. So this is a range where there's no other mechanical test we could do to extract a number like this. So this may not be a perfect number, but it is quantitative and reproducible and has tight error bars. So that's useful. The other thing we can do is, now we have an understanding of what plasticity looks like. Plasticity follows a power law. And so when we have an event like bonding, in these cases here, bonding happens at the dashed vertical line. So that bonding event is a departure from classical plasticity. And that is now abundantly clear, because we can now identify points like these where we start to diverge from the power law behavior as we asymptote out into the bonding condition. And so we're now able to identify the divergent regime, and we can study that divergent regime and try to figure out what's going on in that regime. It's clearly not just a continuation of plasticity. Some new phenomenon is setting on, and we'd like to understand that. So what new phenomenon sets on? Well, actually, this is one of the very first things we tried to work on 3 or 4 years ago when we were getting started, because we noticed that we would take data like this. Here's an aluminum particle. It flies in, it strikes the substrate, and it sticks. Well, we have no idea what's going on right here where it's impacting and touching down. And that touchdown event is critical because something's happening at that touchdown that separates a bouncing impact from a sticking impact like the one shown here. And so what we wanted to do was go just over the edge and look at what happens and zoom in both in space and in time and watch what happens as that particle strikes the substrate and bonds. And this movie is a few years old, and I apologize for that, but it is a watershed moment for this project because, as this video shows, when we watch particles stick, there's a unique phenomenon that comes with that, and it is this splash event that you see here. Particles that stick have little solid state splashes that shoot out the side. So it's almost now like it looks like a meteorite impacting. We have jetting, we have ejecta shooting out the sides when these things stick. And and that's our proposal. So we're proposing that, look, plasticity prevails for most velocities, but once we start to diverge, it's because this new phenomenon of jetting is starting to happen. And now that you have that hypothesis, you can go start looking for corroborating evidence. So lipid data are great, but they're even better when they're augmented by good microscopy. So let's put these things in the microscope and look at them. Here's what happens in the case where you have what I would say sort of classical power law plasticity. Here we have a crater for copper on copper, and it just looks like a crater. There's no evidence that there's any kind of rupture at the edges or jets of material have shot out. So that's what a clean, no jetting impact looks like. Conversely, on this end, when there's very clear jetting going on, this is what it looks like. So this is a particle now with huge lips around the edge, and you can see that material has been extruded up around the edge and shot out of there, right? So that's clear evidence that jetting occurred. And now the interesting question is in the middle. When we diverge from the power law, but before the particle sticks, do we have any jetting? And the answer is we do. So here is a crater. So this particle bounced, but it also left behind jets all around the edge. So indeed, we have evidence now that it is this phenomenon, this jetting at the edges, that is really what's going on in this divergent regime. Yu-Chen Sun, who's actually a new employee there at Livermore, he had this very famous set of photographs that he took because this is now catching the whole thing in the act. So this is for a shot that's in the middle here. It's in this zone where particles bounce, but they still exhibit jets. And so this particle here with a 20 nanosecond resolution, he captured a jet happening, and that even though there's a jet, this particle is still bouncing away. So this is the range where jetting starts, but not enough yet to produce sticking of the particle. So there are two critical velocities now that we can measure, and these are independent measurements, by the way. This is important. We can measure the velocity at which we start to diverge from plasticity, and we can measure the velocity at which particles cease to bounce at all. So we have two different critical velocities that we can now measure and study. I'm going to mention something important before I go on here. So a lot of people, when they see that video of a splash, they instantly go to liquid. They imagine that some liquefaction has occurred. But I want to emphasize that this is not a melting phenomenon. So right now, I'm not talking about melting. In fact, you can do finite element simulations. You can calculate the adiabatic heat that goes in. There's definitely some heating that goes on in these experiments, but there's no reason to think we would get near the melting point of copper. And additionally, if you look at these jet lips here, There is no evidence here that any melting occurred. This doesn't look like a molten and resolidified structure at all. This looks like a plasticity phenomenon. It looks like tearing and extrusion and shearing, right? So we think this is a solid state ejecta projection, solid state splash. In fact, we are of the opinion that what you're seeing here are hydrodynamic jetting events. So the reason we think this is because our geometry is what you might call a convergent geometry, and it's a shock problem. So we have here a particle which is shooting down and impacting a substrate. And in this geometry, we're producing shock waves at the contact, and those shock waves are interacting with the particle and the substrate sort of clamping shut, right? So there's a V-shaped geometry here as these two surfaces clamp shut together. And that geometry is sort of a familiar one in the shock world. If you think of a shaped charge and a shaped charge liner, of course, this is a convergent shock, and it's well understood that the collapse of this V shape leads to a hydrodynamic condition that shoots a jet out the center. Even more directly relevant is an explosion weld. In the field of explosion welding, you take a plate and you put it at an intentional angle to a partner plate down here. And then when you set off this explosion, that V-shaped gets you this convergent geometry, and it produces hydrodynamic jets that shoot out the center. And importantly, in the case of explosion welding, this jet is actually a functional feature of the process. So the hydrodynamic jet sort of cleans off the interface. It crushes asperities and it breaks up oxides and that kind of thing so that you can actually get an explosion bond that is metallurgical. So we see this microparticle situation as just being a micro shape charge or a micro explosion weld. We're smacking those guys together and they're shooting out jets. And in fact, the mechanism then is the same one as in those cases. The shock waves detach from the free surface. We flip a state of compression into one of tension, and you get a jet shooting out in what is, essentially a spall-like process, right? This is almost like a shock spall type process where we're shooting out a jet. So that's the way we view this phenomenon, and we have quantitative tools to study it now. So why don't we go quantitatively work on this and see if we can't convince ourselves that this really is a hydrodynamic phenomenon. So here's the way we've approached it. I'm a big fan of scaling laws because they capture essential physics in sort of a beautiful way. And so what we did is we developed a scaling law. What we said is, okay, look, the jet phenomenon here, this basically happens if we flip a shock wave into tension, and if that induced tension exceeds the local strength, that's when a jet is going to shoot out. So you can write down an expression for the dynamic pressure. This is just a straightforward textbook expression where the velocity goes in there and the density and the speed of sound and so on. But this is the pressure you produce upon impact. You flip that into tension, and so there's some proportionality constant you don't know, but anyway, it's just some constant, so we'll flip it and we'll leave it in there. You rearrange this equation, you keep only a physical root, and you've got a very simple scaling law. If indeed jetting is a hydrodynamic phenomenon, then the velocity at which we see jetting set on will be a function of the speed of sound and the bulk modulus, so elastic properties. And of course, we have to exceed the local strength, which, by the way, you might approximate that with a measurement of Spall strength. So the dynamic yield strength goes in on the top, and the elastic properties here on the bottom. So this is our hypothesis now. We've got a hypothesis, we've got the scaling law. What we want to do now is design new experiments to test it. So the first thing that you might do is you might look for the strength dependence. What you want to do is test materials that have different strengths, or different Spall strengths, if you will, but they have the same elastic properties. So we want to cancel out everything here except the strength. The way we approached that was to take those data I showed you for aluminum, and now if we keep the base metal as aluminum, but we do some light alloying and heat treatment, you can actually go to aluminum alloys, and in an elastic sense, they're basically the same. They have the same speed of sound and the same modulus to first order, but their strength is different. We can strengthen aluminum by 50%, and as a result, and exactly in line with this scaling law, we measure that their critical velocity goes up in proportion. So that linear scaling between strength or spall strength and the critical velocity is validated with those kind of experiments. The second thing you might do to validate this theory is try to get rid of the strength and focus on the elastic properties. And it turns out you can do that reasonably well if you're willing to work on high purity metals. If you work on high purity metals, then the strength is proportional to the bulk modulus. And so this entire term here on the right turns into a constant. And the only dependence you have left then is the speed of sound. So you expect that the critical velocity becomes a function of the speed of sound. And so indeed, when we do a bunch of tests on high purity metals, that's exactly what we find. These guys line up, they follow the scaling law, it goes through the origin as expected. And by the way, that turns out to be true not just for one critical velocity. These data are for the critical velocity to bond the particle. It's true also now for that independent measurement. This is the critical velocity to start a jet forming. So this is the divergence velocity, the velocity at which we first diverge from that power law. Those also obey the same scaling. And so to us, this is really convincing evidence that this is a hydrodynamic phenomenon. And if you look closely at these data, these metals, the speed of sound puts them in the right order and it lines them up. But there's no other material property that would rank them in this way. So these things are not ranking with their strength. They're not ranking with their modulus or their melting point or their density or anything. It is uniquely the speed of sound that puts those guys on the curve. All right, so we're starting to get smart here. We can measure the yield strength from the plastic part of this curve. We now understand that this divergence regime is about the onset of a hydrodynamic effect, the formation of a jet. We can now go a little further and try to understand that bonding process, right? So jetting and bonding go together. Well, what is that about? One way that we've thought about this is by looking at the energy budget. So if you look at these data, everything that does not fall on the plasticity line, that's telling you that there's an excess softening going on. So you're pulling kinetic energy out of the particle. You're slowing it down more than plasticity alone would do, right? So that's what this tail is here. And you can actually quantitatively measure that energy, and we call that the divergent energy. And you can see here for copper on copper, that divergent energy is a few nanojoules and maybe as high as 5 or 6 nanojoules up to the critical bonding velocity here. So that's interesting. We got 6 nanojoules worth of energy we've got to explain, and we've got to link that somehow to the process of bonding. So where does the energy go? So this brings us to the notion of oxides and cleaning up the surface. I mentioned to you that in an explosion weld, hydrodynamic jets are really useful because they sort of clean off the surface. And we know that if we impact a particle on a substrate here, like a copper particle, we know there's a native oxide layer in between, right? This is not metal on metal contact. There's crud on these particles because that's what nature is. So we know that we need enough deformation somehow to fracture that oxide layer, produce individual islands, squirt metal through and get contact between particle and substrate. And maybe that jetting process at the edge helps us sort of squirt oxides out and form clean contacts. But oxide is really important to the phenomenon of bonding. So let's talk a little bit about oxides. So for this phase of the work, I really want to acknowledge, so Jasper you've already met, he's one of our students, and now also Ahmed Tiamiyu. He's a postdoc in the group who really is interested in microstructure and oxide effects. And so we're going to do a lot of microscopy now to understand this. And we also then bring in some microscopy expertise in the form of my other colleagues here, Ji Chen and Jim LeBeau at MIT. So now we've got the sort of microscopy team on the case to look at the oxides. So here are atomized powders of copper. So what we do is we take powders like these and we pick the sphericalist looking ones of them and we go out and we shoot them, right? But what you should keep in mind is that these powders are manufactured industrially. And, it's a reasonably clean industrial process, but there is ample scope for these powders to have surface layers on them. So there's native oxide, there's other potential tramp elements around like carbon. And so we are very interested in characterizing those powders. And so here we're cutting it open and we're putting it in the the TEM and the STEM and the EDS. And we're able to measure now that the oxide layer that we're up against on these particles actually is a thick, nasty layer. It's something like 20 to 40 nanometers thick, big, thick copper oxide layer that it's actually very friable. It has a very low fracture toughness on the order of 1 megapascal root meter. So it's kind of a flaky, thick, nasty oxide that's on these particles. And here's what it looks like after we shoot these particles into the substrate, right? So here is the particle, and then the substrate is down underneath. And if we cut these open and we go look at the interface, we can see how really important the oxide is, because some portions of the interface here are not bonded at all. Like the particle and the substrate never do the coppers meet, right? There is no contact of the copper metal there because that oxide has remained in the middle, and it is fully present and preventing metallurgical bonding. Whereas on the other side, in this case on that side, we have, I guess, higher deformation, because over here now we've broken up that oxide, we've rarefied it, and we have metal connecting all the way through the interface. So this particle here is tacked on by virtue only of a little patch over here on the right-hand side. All right, so oxide is important, breaking of oxide. We know that we get bonding in this regime here, where we start to have the power law divergence and we have jetting setting on. How can we quantitatively connect oxides and jetting and bonding in this regime? Well, here's what we're going to do. We're going to go do some experiments, and we're going to study how do oxides respond in this regime. So let me start with one observation. I'm going to start with really high velocity here. So this is a copper particle hitting a substrate. Bear in mind again that the copper has a big, thick oxide layer on it. And so that's what you're looking at here. When you stick a particle to the substrate and then you look at it in the confocal microscope, this coloration here, this bright orange, that's the thick oxide. So it is visible in this form of microscopy. Compare that to a freshly prepared substrate, which is almost oxide free. This is bare copper. So you've got bare copper, and then this is the thick oxide. All right, so that's what oxides look like in the microscope. Now let's go to the other side of this diagram. Here's what it looks like if I do this impact, but the particle bounces away and I've just dented the substrate. Now you can see we've made a crater, but we haven't got any change in the oxide. It's just a clean, well-prepared substrate. There's no oxide going on. So this is full oxide, this is no oxide. Now we can go to this region in the middle and start to explore it. And here's what it looks like. In between, we see exactly what we were expecting, that in the range where jetting is starting to happen, first of all, you'll see evidence of those jets starting to form around the periphery of the particle. But more importantly here, also around the periphery, look at these patches of rust color. You are looking at oxide flakes that have cracked up on the surface of the particle, and they have detached and fallen out. They've delaminated and they've transferred onto the substrate. So the onset of jetting is now also a moment where we see the onset of transferring oxide. So we are indeed cracking up that oxide layer. Now, if you don't believe this color thing that I showed you, there is other evidence. We can do other types of microscopy, such as in-lens SEM, to see literally flakes of oxide that have transferred over from particle onto substrate. So we're really quite convinced that, in fact, right in that divergent range, right where the velocity goes away from just being sort of conventional plasticity, we're getting a lot of oxide flaking and fracture. So we're big fans of quantitative science, and so one of the things we've done is we've done a bunch of shots in this range, and we've gone in and tried to quantitatively measure the amount of delaminated oxide that we're seeing. And so we do some image processing. We've got an algorithm which can separate topography from color in these images, and so it can literally measure all the regions where it thinks there are flakes of oxide that have fallen off. And we can do that actually quantitatively and with error bars, which allows us to measure it. And so here's a whole bunch of data for a bunch of shots that we've done. All of these lie in that divergent regime where jetting has set on and bonding is about to happen. And we're pretty convinced now that we're delaminating oxides first at the rate of maybe a few dozen square micrometers, and ultimately as high as perhaps 100 square micrometers of delaminated oxide. Now, if you do a little back of the envelope math, actually that turns out to be a really interesting number, because if you know the area that you've delaminated and you know the fracture toughness that prevails at that interface, again, it's on the order of 1 megapascal root meter, that lets you calculate the amount of energy that you spend on rupturing oxide. And what we're finding is that it's something on the order of 1 or 2 nanojoules. So in the case of copper, when we are damping and slowing down that particle, about 1/3 of the total energy getting pulled out is being spent on breaking up that oxide layer. So oxide rupture and breaking is a big part of the work that goes on in order to produce metallurgical bonding. What's the rest of that energy? In our papers, we've looked at a number of different sources of dissipation and how they could come into this. And there's one that I think is very important, but we cannot quantify it. And that is the process of jetting itself. The particle splashes down and we are ejecting out solid matter. And that matter is flying out at some velocity and it has a certain mass. And so it's literally carrying away some kinetic energy with it. And while I might be able to estimate the velocity from our videos, I really have no way to measure the mass. I can't really measure those splashes. This is an open area for research. The best I can do is put an upper bound on it because I know that I can't eject more mass than would account for the full energy budget. So this gets me to the last topic here that I wanted to briefly mention on, and some new collaborators. So it's been really a fantastic pleasure for the past year or year and a half when we've been working with Alison Saunders and Fadi Najjar and the cast of thousands here at Livermore, because the Livermore team talked to us and they challenged us. They said, look, it would be really interesting to measure the splash. Like, we are interested in ejecta in general, and we want to measure it. We want more quantitative work on the splash. How would we do that? And so we started thinking about that. How do you do it? In the case of copper, it's very hard to do because it's so small. We're estimating something like a cubic micron of matter gets ejected. It's just very tiny. And of course, there's a conflation of all the different volumes because the particles are sticking. So when we went forward with this work collaborating with Livermore, we wanted to design an experiment where we would get a bigger splash that would be quantifiable. And so we wanted to focus on a system with a more of a softening response, and we wanted to use particles that bounce away so that they're not part of the math anymore, and we can isolate just what's happening on the substrate. So the experiments that I'm going to talk about today are ones where we've designed for this, and we're using a stainless steel striking pin for these experiments. A lot of this looks similar to what I've shown before. We buy very spherical atomized stainless steel powders. We shoot them at tin. We do this at many different velocities, and we've picked this system where there's really not a strong tendency for the particles to stick. Tin and stainless steel don't want to react with each other. They're not strong metallurgical reactants, so we mostly get bouncing. And if we plot these data in the power law format, we have exactly the same thing we saw over here with copper. So there's like a plasticity regime. This is sort of the classic Wu power law. And now we have a divergence regime. But in these experiments, we've got a really big, thick divergence regime that we can go in and target and try to understand. So let me show you some of the lipid data from lipid raw data from these experiments. So here's a particle that's bouncing. This is at a low velocity. When I go to a high velocity near the cusp, so this is near the breakdown regime now, this is 460 meters per second. And if you squint, you might just begin to see the hint of a splash here. In fact, I'm going to blow this up for you so that you can, maybe now you don't need to squint, but you can see, indeed, there's a little splash in this video. So at 460, we start to see a softening and ejecta are produced. By the time we get to 660 meters per second, you don't need to squint anymore. It's a pretty convincing splash that lasts for dozens and dozens of nanoseconds. And at 920, it's not just a big splash that lasts a long time, but we actually see ejecta flying away for like microseconds, like huge, long falling action from the giant explosion of ejected matter. So we can go in and we can look at these guys. We can see things that bounce gently. We can see one particle manage to embed itself, but that's an outlier case. And actually, we can zoom in right where we saw that divergence. In fact, that was at 460. So here's a zoomed in view. And I can tell you now that the splash in this case is not about hydrodynamic plasticity. This time the splash is associated with melting. And it's unequivocal from these micrographs because this is the first speed at which we saw the little splash. And now look at the ex situ evidence here. These structures, they're rounded, right? This is molten tin that it melted and it beat it up and it re-solidified in what is clearly a solidification structure all the way around the rim. So this is a melting related phenomenon. And as we go to higher velocities, we see that it's not just around the rim, but it penetrates deeper and eventually all the way in at high enough velocities. So extensive surface melting where the particle has impacted the tin substrate. Why did it melt? I'm going to spare you some details here and tell you that our shock pressure is actually pretty low. It's only 16 gigapascals, so we don't think this is a pressure or pressure release related melting. This melting is because of plasticity. We are simply deforming this thing so fast and so hard that we are adiabatically heating it up to the point that it melts. All right, so let's now analyze this divergent behavior and try to measure a splash. So the first thing I might do is the same thing I did for copper. So I told you before that I've got a divergence from the power law. So there's excess energy being drawn out of the particle in this regime, and we can go ahead and quantify that. So here is the excess energy loss, which we are now attributing to the new physics that onsets once melting is present. In fact, if you want to be bold, you could say, hey, look, the only thing we know for sure that's new here is that there's melting going on. And so maybe all of this extra spent energy is due to melting. So you can do sort of an upper bound calculation, if you will, and you could say, look, every last bit of this energy is going into melting. It's going into the heat of fusion of tin. And if that were the case, then it's a simple linear conversion to figure out how much stuff melted. So here it is. Here's an upper bound guess. This is the maximum amount of stuff we might have melted at all these different velocities. At our highest velocity, we might have melted up to 30 cubic microns. All right, so that's an expectation now. By the way, in copper, when I was talking about jets in copper, we were talking about 1 cubic micron. Those jets are teeny tiny. This is a giant splash. 30 cubic microns of material could have melted with this energy budget. But now, because we've designed this experiment so that there's no particle sticking there, the particle flew away, we have an independent way to come at the volume measurement. We can go in and we can use quantitative confocal surface measurements, and we can literally measure the volume of lost matter. Because we can measure the amount of pileup, we can measure the depth of the crater. We do that fully in 3D, and the difference between red and blue here gives you the amount of lost matter. So it's a volume conservation from a flat sheet. You can calculate exactly how much matter you lost. And so now for every single shot, we can go in and we can tell you exactly how much tin was lost after we shot these particles. Look how big they are. It's a staggering amount of volume loss, staggering. In fact, at the highest velocities, it's hundreds and hundreds of cubic microns of material. It's almost as much volume as the particle we shot in the first place. So we're talking about almost a giant ball of material has been ejected in these splashes. Huge, huge volumes. And that is really interesting because I showed you the energy budget. If the energy loss went into melting, this is how much could have melted. And this is how much got ejected. So the Livermore team was right. There's definitely gold here. Like this is a really interesting area to study because now we have a very interesting result. When we watch these giant splashes, even when we know that they are involved in melting and melting has apparently lubricated the splash, nonetheless, we now know that the splash is mostly solid ejecta. We're ejecting solid tin. So that's a really interesting result, and we hope to keep working on this topic going forward. All right, I've talked too long, so I'm going to bring this to an end. The last thing I was going to mention is that lipid measurements and microscopy, I've already shown you a lot of examples where putting microscopy and lipid together is really powerful. I wanted to mention that you can also study microstructure. And I'm a materials scientist and I like microstructure. And we can actually do tests at very high strains and very high strain rates and study microstructure evolution in new ways. And I won't go into this at all, but when you put advanced microscopy together with lipid, you can learn all kinds of new things about deformation mechanisms in very extreme conditions. And that's one of our topics for future work. All right, I'm done. You've met everybody on the slide at this point. You know what we're up to. I do want to acknowledge the funding from all the people listed here, and especially from John Vetrano's DOE BES program, which has really got us working hard on these fundamentals and helped us to collaborate with groups like Livermore. Thank you for your attention. If you remember nothing else today, I hope it's that lipid plus microscopy is an amazing quantitative tool for high rate mechanical studies. And I will stop there and be happy to answer any questions.
Thank you so much for the wonderful talk. So you could please enter any questions you have in the chat field or let me know if you have questions. In the meantime, let's thank our speaker and give a nice applause.
Thundering virtual applause. Thank you so much.
Yes. We already have a question from Matt Hill. Thanks for the great talk. Is there a volume change associated with any phase changes during or after the impacts?
So the only phase change that I'm willing to attest to here is the one that I showed you in tin, where we know that we're melting it. The volume change on melting tin is not large, and critically, it's reversible, right? So none of our observations, we don't actually capture the volume change in any of these measurements. We capture it after it's resolidified. So there's no permanent volume change. There's also no reason to expect any solid state changes in any of the materials that I showed you.
And there's a comment from Carlene Maskley, who just says, great talk, Chris.
That's my kind of question.
Yeah. And Morty Rosen says, wonderful talk, thank you. Can you slow down your particles and see if your data shakes hands, in quotation marks, with the data from the literature?
Can we slow it down? We can. So, in fact, as part of our work with Livermore, we did some things where we tried to slow it down, and we can get the velocity down to a few dozen meters per second, which gets you into the same velocity range as some other micromechanical tests. But our strain rate is still a few orders of magnitude high because we're so small. So it is a significant research project to get between 10 to the 7th and now 10 to the 4th, where like a Kolsky bar would hit, right? So there's a 3 order of magnitude gap there, which I think there's some innovation needed. It's not just a matter of slowing down the velocity. We have to also change the size scale in order to get across that gap. And I think it's a great suggestion. It's a great idea for future work.
Thanks. There's a question from Lauren Benedict. It says, near the beginning of your talk, you mentioned that your inferred hardness had a 2-regime structure, where the high strain rate regime gave a very increased hardness. Is this related in some way to what you described later on in your talk, i.e. bonding between the projectile and the target, or something else?
I think something else is the answer. So I'm not sure I want to weigh in with a definitive answer because I don't think the world knows why there is an uptick in rate hardening at about 10 to the 4th per second in copper or in iron. I don't think we know, but I don't think it's related to bonding. I think it's inside the metal. There's some new physics going on related to phonon drag or something that gives you a change in rate hardening, but I wouldn't want to speculate more.
And from Jonathan Lind, thank you, really nice work. You motivate that lipid can provide high strain rate strength data to address questions such as the upturn phenomena, which is directly a signature of the strain rate sensitivity of materials. However, the EPP scaling model you showed fit the data to a collection of tests where the characteristic strain rates are large and vary by a few orders of magnitude. How does coding one strength or hardness value from the EPP scaling model over a large range of high strain rates remain consistent with the strain rate sensitivity picture of the material, especially at high rates, where the effect is even more pronounced?
Yeah, that's a very smart question. I'll give one parenthetical comment and then I'll come back and provide. I don't think I have an answer to this, but I'll come back and say something. The parenthetical comment is that when I change the velocity of these shots between like 100 meters per second and a kilometer per second, like that's it's an order of magnitude. We fit over an order of magnitude. That's actually a pretty tight range for a strain rate property, which we map over 10 orders of magnitude. So I can measure a hardness, and even though I'm measuring it over an order of magnitude, and those are all pretty tight, right? When I compare them across 7 orders of magnitude, that turns into one data point. And so that excess high hardness that's a real effect. It's not like some artifact of some shots being faster than others. So that's an aside. And then there is this bigger question of those hardness values. There are no fitting parameters for those hardness values, right? There's no fitting at all. That doesn't rely on the Wu model. So I can regard that as one measurement of strength. So I have a hardness. Then I can do a bunch of shots and use the Wu model, and I get a second independent measurement of hardness or of strength. And how those two connect, that is still a mystery. In the world of hardness testing, we call the ratio of yield strength to hardness, that's the constraint factor. No one, to my knowledge, has explored the constraint factor at these very high rates. So you're definitely asking a smart question and you're poking at a really open area that I hope to address in the coming year or two.
So from Carlene Mascali, have you looked at what happens when the particles hit the substrate at an angle?
We have. I so the Lippitt team has shot so many things at so many other things that there's like an overwhelming amount of stuff that we have done, which I'm not able to include. And angled shots is one of those things. So we've done quite a bit of that, and we have a lot of data, and we don't yet have a convincing understanding or explanation for all those data yet. And that's something that we're working on now. So if you ask me that again in a year, I hope to give you like a full seminar about it.
Sounds good. From Allison Engwall, hi Chris, great to see you. If you look at like metal lipid measurements for particle surface pairs with less robust oxide layers, do cleaner surfaces have a more abrupt transition from rebound to sticking?
Yes, so this is another thing I didn't have time to show, but we did a whole giant work in aluminum. Aluminum has a thin and very tenacious oxide layer, and we studied different aluminums where we intentionally changed the thickness of that oxide layer. And your question is dead on. So if we use materials with thinner oxide layers, we get earlier bonding transitions. It's easier to break them when they're thinner. So yes, the logical extension of all the things I showed you does turn out to be true. And now that we understand it, it tells you what direction to go. If you want to delay bonding or promote bonding, we definitely can sort of diddle with the oxide layer to help make that happen.
And here's a question from Tej Timkar Omanath. Thanks for the great talk. In your experiments with stainless steel particles, do you mind explaining how you determined that the ejecta was in fact solid and not partly melted liquid? Or were you measuring the redeposited material that had already solidified on the substrate?
No, so I apologize if that went by too fast, but basically it's a mismatch, right? So we know directly from measurement that we've ejected 800 cubic microns of matter. So we know exactly how much matter we've ejected. Then from a separate measurement, when we know how much energy was available to do melting in those experiments, and the energy available to do melting could only melt 30 cubic microns. So we're ejecting 800, but there's not enough energy to melt more than 30. QED, right? Most of it could not have been melted. Most of it had to be solid.
So I have a related question, more conceptual. So I understand that argument, but just like what does it mean when the materials has to deform so much in order to splash, but it's still a solid? Like, is this
Yeah. So,
what's happening to the bonds here?
well,
What's
so
going
here's the
on?
way. Yeah, I have a mental model, but don't take this to the bank. But here's how I view it in my head. So the particle strikes. you get incredibly rapid deformation at the interface. And the metal starts to liquefy in regions, but it probably does so in bands, right? Where dislocations are slipping together, you probably get little pockets or bands that are melting first. And once you have liquid in there, now that has a zero tensile strength, right? So you've got a whole bunch of like zero strength material, and it may be woven all around other solid portions of the material. And so now the zero strength stuff is unstitching the solid, and it's sort of letting other particles somehow rip free. They don't have to melt; they just go along for the ride somehow. That's my mental model of what's happening, but we don't know. We can't see it.
There's probably some sort of liquid like layer or something in there that's letting things smear around.
Yeah.
Okay. I guess one more question from Andrew Hoff. Hi, Chris. Have you done any work combining cold spray with grain boundary engineered materials? If you had a high enough bonding impact temperature, could something analogous to a nanophase separation sintering be possible to improve bonding? Or would the oxide phase or timescales preclude that scenario?
That's a good question. Yeah, so it is sort of an interest of mine to study chemical reactions during these impacts. The timescales are very short, as the question suggests. So, I mean, you've got like, I don't know, a couple hundred nanoseconds of total action for some kind of reaction to happen. But that could be enough time. So there's time, there's heat, there's pressure. Um, we have done some cases where we like shoot mismatched pairs together, so like copper and aluminum, and we definitely see intermetallic reactions at that interface. So it's possible to trigger reactions. It's possible to trigger phase separation. I'm not sure. I can't say that it's well studied, but it is a sort of a pregnant topic, I would say. So it's a good question.
Thank you. Any more questions? And if not, I would like to thank our speaker again and hope everybody enjoyed the talk and hope to see you back next week.
Thank
Yay.
you, everybody. Take care.
Thank you. That was a great talk.
Thank you. It was my pleasure.